All right, in this worked example, part B here, you can kind of see the setup and I've zoomed in on it, but part A was state the principle of conservation of momentum. And we're going to apply that principle of conservation of momentum here in order to solve this. And so what we want to do is solve for this angle theta, and we want to solve for this velocity v. Okay. So the initial momentum in the x direction before a collision is equal to the final momentum in the x direction after the collision. The initial momentum in the y direction is sort of absent, right? There is no y component of momentum, but we see that over here. And so the initial y component of momentum equals the final y component of momentum, right? So we have to keep those ideas in mind in order to sort of, solve for this. The question actually, we were talking about this a moment ago, gives you a clue. It says, by considering the components of momentum at right angles to the direction of the initial path of ball A, calculate theta. So that's giving you a clue as to how to solve it. The right angle to the initial path would be sort of this direction here, right? So there's a component of ball A's velocity that moves up, and there's a component of ball B's velocity that's moving down. So there's a down momentum and there's an up momentum, and they're equal to each other because the initial momentum in the y direction is 0. So the initial momentum in the y direction equals 0, and you could say, well, it's the sum of the individual momenta. So you can say, like, well, the velocity of A in the y direction is 0, the velocity of B in the y direction is 0, and so their individual momenta is 0 in that direction. So we sum them up and sort of think about it like that. And so that's got to be true over here. The after momentum has to be 0. So the positive momentum of this vector is equal to the negative momentum of that one. Let's just resolve the velocity. So if the angle here is 30 degrees and the velocity is 3.5, and this is the side opposite this 30-degree angle, then we could either calculate it as the sine of 30 degrees times 3.5 meters per second, and then realize, oh, it's pointing down, I need to make that negative, because we've aligned, or we've measured the angle sort of relative, or we're sort of opening the angle down this way. The positive x-axis goes like this, and so we could also substitute in that angle, and you could take the sine of 330 degrees times 3.5. If you're not familiar with the mathematics of, how is the sine of 30 and the sine of 330 related, do that in your calculator real quick and realize that by always orienting your angle to the positive x-axis, the calculator deals with the vector nature of that velocity for you. In other words, sine 30 is a half. In other words, half of the velocity is acting in the vertical direction, but sine of 330 is negative a half, right? So by putting in 330, it's reminding you, like, oh yeah, it's going down, right? It's like down is, is negative. That's the convention we adopt, that sort of sign convention there. So if you didn't already sort of know that, check it out in your calculator, or just sit tight there, YouTube. Don't worry, I got you. There's a scientific calculator. And I'm going to take, let's see, I got trigonometry here. So there's a sine. So I'm going to put 330 in there and take the sine of that. And you can see it's negative a half. Is one of the many universities here in the state of Florida that you can apply to today, but make sure that you know your physics. I don't know if that picked up on a mic. So well done there, okay? Maybe I'll get a sponsorship. This worked example is brought to you by Dairy Queen, which will maybe give me free blizzards one day in the future. That's my hope. All right, so what's half of 3.5? 1.75. So 1.75 meters per second acting down. And so it's like, that's the velocity in the y direction for ball, B, however you want to sort of keep track of that. What we want is the actual momentum of that, though. And so the momentum is mass times velocity. So we'll multiply 1.75 by 12. And realize that there's 21 units of momentum acting down, which means immediately there's 21 units of momentum acting up. Like, that's the approach that we took here. We said, if we can calculate the down momentum, then that's the up momentum here. And now we know enough about this triangle to calculate theta. It's like one, sort of idea leads to the next. What are you given? we're given everything about this object, so we should be able to calculate and figure it out and relate it back to something that we want to know. My advice now is to realize that like this is momentum, kilogram meters per second of momentum in the vertical direction. Well, how much momentum is going in this direction? In other words, we can't use like a velocity vector for the hypotenuse, but a momentum vector, for the vertical component. We've got to have a momentum vector triangle or a velocity vector triangle. So rather than like trying to pick back out the vertical component of velocity here, I think it's easier to just multiply this velocity times this mass and get the momentum, in that direction, right? So 6 times 4, 24, right? So we know that the momentum of this object is 24. We know that the vertical component of momentum is 21. And if you can make it sort of that far, hopefully by now you know the trigonometry to solve for that angle, right? It's like, okay, we know now the opposite. We know the hypotenuse. The hypotenuse was everything but given to you, right? They gave you the mass, they gave you the velocity, just multiply them, knowing the definition of linear momentum. One of the learning objectives, belonging with this chapter. So something with a hypotenuse of 24 and a side of 21 has what angle here? Well, that's going to be the inverse sine of 21 over 24, right? Opposite over hypotenuse, inverse sine solves for the angle. So if you type that in your calculator, I think you get 61 degrees. So anybody that was able to get 61, well done. That's what I think the answer is, but we can always check the mark scheme, which we'll do in just a moment. Let's use that answer to show that this velocity is 12. So if we read on to the question paper here, and I'm just going to scroll back up a moment, but I want to show you. So we calculated theta by considering the vertical components, right? They don't say vertical components, but synonymous with components of momentum at right angles to the direction of initial path. The initial path being horizontal, the right angle to it is vertical. Use your answer in one to show that the initial speed v of ball A is 12. And the final part here is by calculation of kinetic energies, state and explain whether the collision is elastic or inelastic for a final 3 marks on this one. And so those are the remaining parts of this that we're going to consider now. There. Easy come, easy go. All right. So we calculated this angle to be 61 degrees. Okay, when all was said and done, right? How is this velocity 12? Let's just calculate the velocity. So because we know the angle, we could calculate the x component of this, momentum for both of these, right? Because we already knew sort of everything about this. And so for this one, we're going to have a final momentum in the x direction, for ball A. We're going to have a final momentum in the x direction for ball B. And you could put the B as a subscript or, do it like this or just in your figure. So however you want to keep track of sort of what we need to do. By calculating these, we could sum them and realize it's equal to this momentum. All the momentum in the x direction came from ball A. It's like the ballistic pendulum. Here's a target at rest that's more massive. We crash this one into it. But instead of letting the pendulum swing up and using energy or something to deduce the initial conditions, we use the law of conservation of momentum to sort of watch the after effects, like a ballistic sort of problem, like, oh, anything that moves off like this in this direction must have the other thing moving sort of like this. So this one is going to be the cosine of 61 degrees times 6 meters per second. That would give you the x component of velocity, and then multiply it by 4 to get the momentum, right? So don't forget that momentum is mass times velocity. The cosine of 61 times 6 is 2.9. So we get sort of a velocity here of 2.9 meters per second multiplied by 4 to get a momentum in the x direction. So this is sort of after the collision of 11.64. So this is AX sort of after. So B, we've got the cosine of 30 degrees times 3.5. So again, cosine 30 times hypotenuse gives us the x component. So this vector here has an x component of 3.03 meters per second. When we multiply that by 12 kilograms, we realize that the momentum, okay, so this is like momentum final, momentum initial, is 36.37. 11.64 plus 36.37 is about 48. So there's 48 kilogram meters per second of momentum in the x direction. Okay, so that's just the x component because we only use the x components of velocity. The initial momentum is mass times velocity, 4 kilograms times some unknown velocity, which is suggested to be 12. So 4 times some number equals 48. You couldn't already sort of anticipate, okay, dividing side by 4, sure enough, you know, V is 12. Now, this rounds to 48, but the actual number in my calculator is 48.01306. So when I divide that by 4, you actually get sort of a calculator value, V equals 12.0032, which is so close to 12, right, that it rounds there. So once you deal with sort of significant digits. But showing this sort of working here in your journal removes any doubt that, you know, like you didn't retro engineer the conclusion. If you start with 12 because they tell you that the velocity is 12 and you sort of work sort of backwards, sometimes that's helpful to sort of figure out the physics if you're at a loss, but you would never really get to maybe this answer right here, which you sort of get by just working through it, you know, the way that, you know, you sort of should. So just calculate what the velocity is and then compare it to what they said. It's like, oh yeah, 12.0032 is about 12. So I showed that that's correct. All right, you may recall that they asked us to determine whether this collision is elastic or inelastic. And so we should be able to do that easily. 1/2 mv squared, 1/2 mv squared for A, 1/2 mv squared for B, right? So we have sort of before and after. There's zero kinetic energy from this guy because its velocity is 0. And it says by, you know, comparing the kinetic energies. 1/2 4 times 12 squared, right? We know that the units are going to give us joules because we're in kilograms and meters per second. So we can realize that there is 144 times 4 times 1/2, or 288 joules of kinetic energy in this system initially. Now, energy is neither created nor destroyed. But just because it doesn't show up as kinetic energy doesn't mean it's sort of destroyed in the universe, right? We're here trying to say, well, if the kinetic energy is all still there, then that's a perfectly elastic collision. Right? So we know everything about this. 1/2 4 times 6 squared plus 1/2 12 times 3.5 squared. So see, like the velocities were given, the masses were given. You have everything you need to know to do that last part of it without knowing theta, you know, or even calculating V, because they give you it's 12. You know, so that those last couple of marks are within reach, even if you were sort of stuck on some of the first parts of it. So keep that in mind too. 6 squared is 36 times 4 times 1/2. So there's 72 joules of kinetic energy in A. 3.5 squared times 12 times 1/2 gives us 73.5 joules in B. So they basically have the same amount of energy. You know, this one's slower, but it's more massive. 73.5 plus 72 is not 288. And so we can conclude what? It's an inelastic collision. It's somewhat inelastic. It's not perfectly inelastic because they don't lock together, but some of the kinetic energy is lost. It's in other forms. It's transformed. It's very likely that there was a sound that was made, right? When those objects collided, that sound costs energy. Those objects are hotter, right? You know, objects crash into each other. It heats up the atoms, you know, so that costs energy, temperature, thermal energy. So usually collisions are somewhat inelastic. We usually lose some of the kinetic energy to other forms like deforming materials or sound or heat are the typical forms of sort of energy there. So you kind of expect to show this unless they were like gas particles, right? We say that gas particles in kinetic molecular theory collide with perfect elasticity. This is Dr. Schleich, living the physics life. We'll see you next time.